2. So, and I should say from the start that this is not a topic I would normally give a talk on. I'm only peripherally involved with the work, but I thought that it's something new coming out of our institute, and it is so germane to the overall subject of the workshop that I thought people would be interested in. So I am very slightly involved. Here's my initials down in the down towards the bottom of the credit line. But basically, this is the work of several groups in my department, and it's led by mostly by the young guys. So these 6 people here are the main players. Christoph doesn't quite count as young anymore. But the corresponding authors on the paper are Seung-Yoon Kim and Elena Hassinger. Then we have some more minor authors all from our institute, including me. I was kind of drafted in late. But then we also have a really nice theory collaboration going on with Daniel Agterberg, and at my request, he's joined this talk because while I could answer some questions about the theory, I certainly can't answer most of them. And so we thought it would be a service to the audience to have him around. But please, I mean, I'm very excited about this work, but please remember in the future, don't associate it with me, associate it with the people who really led it. So what I'm going to do is to tell you about the basic properties of cerium rhodium-2 arsenic-2. Then I'll talk about superconductivity and this very, very unusual phase diagram that we have for it. And throughout the talk, really, I'll be trying to outline why we believe Rashba physics plays a significant role in determining the properties. The final section is just there as future work to emphasize that while I'll talk to you about some aspects of the superconductivity today, there's still a lot that we don't understand about this material. And it looks to have very rich normal state as well as superconducting state physics. So it exists in the understandably named 1,2,2 structure common to many cerium-based compounds. But one of the things I've learned many things on this project, but one of the things I've learned is that there are 2 polytypes or so of this structure. The most common one that most cerium materials would exist in, and many other materials, is of I4-MMM symmetry. But this one exists in a different, slightly different structure, P4-NMM, and I'm not going to tell you what the significance of that is right now, but I certainly will be doing so later. The compound was first reported in 1987, but I don't think any single crystals were grown, and Seung-Yoon succeeded in growing crystals of it from a bismuth flux. Now, he did this about 2.5 years ago. We've been working on this for a long time because we wanted to really establish a certain core number of facts before we started talking about what we were doing, and I hope that'll become clear to you as the talk goes on. So first of all, now I'd just like to give maybe the heavy fermion specialists, if there are any in the audience, a bit of a background of the basic properties. If you just look at the resistivity, you see that you're dealing with the classic signature of a Kondo lattice system. So you have this hump in the resistivity as you go from localized spin state to a coherent state where the F electrons go into the Fermi surface. The Kondo temperature is about 40 Kelvin. The material in the normal state is heavy, definitely a self-respecting heavy fermion. And not only is the electronic heat capacity large at, say, 8 or 10 Kelvin, it's then growing quasi-logarithmically as you go down towards lower temperatures. And that's seen empirically in many, many heavy fermion systems if they're tuned to quantum criticality. So this suggests that this material is near quantum criticality in ambient conditions. If you integrate that heat capacity up, you get to a magnetic entropy, which is slightly unusual because the magnetic entropy saturates, but it saturates at R log 4, not R log 2. And what that's telling us is that the 2 lowest lying crystal field doublets are very close, making a quasi-quartet. And again, that close separation of about 30 Kelvin isn't so usual, particularly in cerium compounds. I'm not going to labor the point, but it's just part of the background physics of the material. What interested Xungheng the most was that when he took it down to low temperatures in various ways, but shown here spectacularly with the heat capacity, you see a very big transition, very big feature in the heat capacity, a big heat capacity anomaly corresponding to superconductivity, which is confirmed by the fact that it's coming at the same temperature as the midpoint of a susceptibility transition. There's another feature also in the heat capacity, and it looks quite small on these axes, but it's distinct and resolvable and followable. And it has, intriguingly, at best, a very, very weak magnetic signature so associated with it. And so that and a few other ways that it behaves makes us wonder whether it's the signature of some kind of multipolar transition. But again, this is just all background stuff for the purposes of the talk today. It's trying to tell people roughly what the background phase diagram of the normal state looks like, from which the superconductivity condenses. Well, the rest of the talk is very much going to be about the superconductivity. So here you see it has a modest TC, 270 millikelvin. And one of the first things that you do when you have a new superconductor is to measure its critical fields. And here we're looking at the critical field achieved when you apply it in the AB plane. And you can see it's not so remarkable, but it has a slightly strange shape and a relatively large value. 2 Tesla is a big critical field for a material with a transition temperature of under 300 millikelvin. When you then rotate the field to the C-axis, the anomalous behavior becomes really acute. So there is the AB plane data replotted on the new axes. It's very anisotropic, and the critical field is of order 15 Tesla for a 270 millikelvin superconductor, and that's absolutely enormous. That was a huge surprise. So that's the data that we had for a year or two while we tried to chase down what the underlying physics of this might be, and now we're in a position to talk about that. So to give you an idea about just how big those numbers are, here's a global plot that I think Elena Hassinger put together, where she plotted HC2, mu naught HC2 divided by TC for a whole range of unconventional superconductors and interesting superconductors. And what you see is that the C-axis critical field in these units of cerium, rhodium-2, arsenic-2 is the biggest, as far as I know, that's ever been seen. Right, so you have some others with huge fields. You really wonder, why on earth this is happening. And I'd say the 3 key things we want to know is, why are the critical fields huge? Why is there such a large critical field anisotropy? And the third thing I hadn't talked about before is, why is there this pronounced kink in the critical field curve for the field along the C-axis? So all of these are unusual and surprising, and we wanted to see more. So in order to discuss that, because it's kind of a mixed audience of mixed background, let me just remind people of the factors that limit the critical fields in superconductors. There are always energetic balances, but they're balances between different energetics. So if you have what are called orbital effects, that's the critical field being determined by an energy balance between the field energy of making supercurrents and the superconducting condensation energy. If you try and the field gets too high, the field energy gets too big and you go normal. That's a famous formula there, relates what's called this orbital upper critical field to the flux quantum divided by the coherence length squared. And in almost all known superconductors, that is what determines HC2, because the coherence length is big, so the critical field is small. But in heavy fermions are special because the high effective mass gives them an extremely short coherence length, so the orbital limit can be very high indeed. And in many heavy fermion systems, it's known that it is not the thing which limits the upper critical field. What often limits the upper critical field are spin effects. So, and this is often known as Pauli pair breaking. And it's related to Zeeman energy of spin polarization. So a spin singlet superconductor is a fundamentally non-magnetic object. You're locked into a zero net spin case. So a spin singlet superconductor has no polarization. It has no Pauli susceptibility. So if the field gets high enough, the energy gain that you can get from doing the standard normal state Pauli polarization will overcome the superconducting condensation energy. And in a traditional superconductor, that gives you a standard superconductor, that gives you a famous expression where you express the Pauli limited critical field as 1.8 times TC. And this is known as the Pauli limit, and it's used very frequently as a guide for whether you have unconventional things going on with your superconductivity or not. So here, what I didn't show the first time I showed you this plot, or didn't highlight, was this dotted line. But this dotted line in these units is the Pauli limit. So most of these superconductors were chosen because they violate the Pauli limit, but the red colored ones violate it very strongly indeed. So how can this happen? How do you think of circumstances in which you could violate the Pauli limit in a superconductor? Well, the most famous one is to think about the superconducting state. If your Cooper pair is not spin up, spin down, but equal spin paired component of a triplet, then you don't need to break the pair to polarize the spins. So there's no longer this competition between spin polarization energy and superconducting condensation energy. So strong violations of the Pauli limit are almost always associated with putative triplet superconductivity in people's minds, and certainly in my mind until I started working on helping my colleagues on this project. But importantly, there's another way, and Daniel was one of the source authors on pointing this out. So if you go to a low symmetry, non-centrosymmetric crystal, then you can have allowed Rashba spin orbit coupling. And the way I think of it is that the Rashba spin orbit coupling gives you a spin texture. You get spin split Fermi surfaces with a spin texture rotating around the Fermi surface. In some senses, those are details. The point is that the Rashba energy scale is locking the spin to the momentum in some way. And by locking the spin like that, you're reducing its polarizability. So the bigger the Rashba term, the less polarizable the spins are in the normal state. Therefore, the weaker their competition with superconductivity. So there's two mechanisms here. One is an unusual superconducting state, and the other one is an unusual normal state. And what Daniel and colleagues did 15 years ago was to show that, that the unusual normal state physics was a key player in dictating the critical fields in non-centrosymmetric superconductors. So, and it turns out that all three of these red players here are non-centrosymmetric. However, confusingly, if you look at the global symmetry, cerium rhodium 2 arsenic 2 is centrosymmetric. It has an inversion center. It's not, it is globally inversion preserving. But it isn't inversion preserving locally. So there's an inversion center in between the two ceriums here. I haven't drawn the structure the whole way. But if you go locally and you think, so that cerium site is not equivalent to that cerium site in this structure. And if you just look for illustration around this cerium site in its local environment, you see that there's not an inversion center with respect to the arsenic and rhodium because it's in this unusual P4 NMM structure. And that means that the local point group is C4V, which is the same as the global point group would be in a globally non-centrosymmetric superconductor. And when Xionghyun and Elena and colleagues were looking around in the literature, beginning to think about this, they saw some work from Manfred Siegrist and Janusse's group, where they had done very idealized models about multilayers, but they had similar ingredients of local inversion breaking to what might exist in cerium rhodium 2 arsenic 2. And what's really intriguing, it's always helpful for us when these guys draw pictures. one of the things they drew was a predicted critical field curve with a kink in it. But much more than just the kink, they said that kink is resulting from a phase transition line sitting in the superconducting state. Now, I'll fully tell you at the end of this talk, phase transitions, properly established thermodynamic phase transitions within superconducting states are very rare, right? And so and they certainly aren't ever seen in these materials which are globally centrosymmetric. So we thought that before making a claim, we really had to look very carefully about whether we had this physics going on or not. So there's the key question. Is there a transition in the superconducting state in cerium, rhodium 2, arsenic 2? I wouldn't be telling you, framing it like this if there wasn't. And it turns out that my colleagues went and did very careful susceptibility, magnetization, and magnetostriction measurements within the superconducting state. And you can just follow this dotted line. You see that there are, pronounced anomalies. These aren't these are very well-resolved cusps and anomalies in the susceptibility and a cusp in the magnetostriction, all coming at a similar field. And that's because the phase diagram of cerium, rhodium 2, arsenic 2 looks like this. There's definitely a thermodynamically established almost horizontal line here, which is a phase transition separating two different kinds of superconductor. Okay? And as I say, that's only been seen a couple of times previously in the whole history of superconductivity. So we were very gratified to see that. And that observation experimentally is the main experimental part of this talk. Whether or not the theory is right, of course, Dan's here, so the theory is right, that I'm going to show you in a second. We have an experimental result here. So we got in touch with Dan, and we told him about the old work which he knew of course, by Segrist. And he agreed that there was a chance that this kind of physics could play out in cerium, rhodium 2, arsenic 2. So what he's written down here is the most general Hamiltonian that you can write for this material with its symmetries if you have a Vanier function centered on the cerium site. And so that most general Hamiltonian allows for in-plane hopping. It allows for a Rashba spin orbit term with a strength coefficient alpha sub r. It has these interlayer hopping terms. And it has an Ising-like spin orbit term, but the Ising-like spin orbit term is fourth order here in the hoppings. So we believe there are very good reasons that it will be small, and in the analysis that follows, we set it to 0, or Dan set it to 0. So when you study the remainder of this Hamiltonian, you think what it's going to do in the normal state. It's easiest to visualize that if for the moment we just set the interlayer hopping to 0 and think only of the Rashba term. Because you're only locally and not globally centrosymmetry breaking, inversion breaking, what you end up having is you have no net Rashba circulation in the material, but you have one direction of Rashba circulation associated with these cerium sites and a second direction of Rashba circulation, a counter direction associated with these cerium sites. And they're related through the global inversion that exists in the material. So if you now turn on the c-axis hopping, you turn up the coefficients of these c-axis hoppings, what you get is that simple picture is going to mix. You're going to get mixing between the bands that have given this counter circulation, but nothing spiritually changes about the argument. So the basic arguments of what you can expect survive this mixing, but it straight away tells you that you're probably going to find physics in a model like this that in some ways will be reflecting an energetic competition between the Rashba scale and the mixing scale. And when Dan analyzes the possibilities for the superconducting state, that is exactly what you see. You find that there are two possible ways that so we make the assumption, which is reasonable for cerium compounds, that in-plane superconductivity is spin singlet paired. And then you have two choices about how that singlet superconductivity exists in these layers in this material. You have a completely even parity state where the gap is the same magnitude everywhere, or you have an odd parity state where the gap function reverses sign from layer to layer. Now, there's a lot on this slide. I mean, it's correct, but I don't want to, over explain or give too many details. But the important things are the following. Dan can show that for that assumption of singlet pairing, the even parity state always wins in zero field. He also produces this pattern of the way that Pauli limiting could occur in the material. And without going into detail, this pattern that he's produced here matches the observations very well. It looks extremely plausible in relation to the observations. And then particularly when you're looking for the field along the z-axis, there's this key point. You're predicting a strongly enhanced Pauli limit for the even parity state, but the odd parity state is actually predicted to have no Pauli limit at all. So you can imagine getting into a situation where as you apply a field, you kill the even parity state at its Pauli limited upper critical field and enter the odd parity state, which is eventually orbitally limited. And that gives you then this natural possibility of a field-induced transition. And if we put all that together, what we get is that here's the data, and here's not really a fit, but a prediction from this kind of model Hamiltonian with this particular choice of parameters, which happens to make cerium, rhodium 2, arsenic 2 an ideal manifestation of this earlier theory by Siegrist and Janissy. And what that tells you is that this phase transition is a phase transition between the even parity and odd parity states at finite field, at least within this picture.
And in 3 minutes.
3 minutes, yeah, I'm going to finish, don't worry. So, it's always nice to refer back to older literature, right? It's always fun to do that. I've come to realize in my career that it's never the end, right? There's always something earlier. And this is quite a story because there's a one-page paper by Phil Anderson from 1985 where you have to read it twice to realize that's what he's done, but he essentially outlined the possibility of this odd parity state existing. He didn't talk about the even to odd transition or anything, but he did outline the odd parity state. I looked up yesterday, Phil Anderson has been cited 90,000 times in his career. And of those 90,000, this paper accounts for 10. So this is arguably, Piers Goldman says, arguably Phil Anderson's least cited paper. But, when you go back, it's hard to find much in solid state physics that Phil Anderson didn't think of before anybody else. So now I'll just close by talking to you about the rarity. The idea of multiple, so you know that helium-3 has a multi-phase phase diagram. And when you think about unconventional superconductivity, you think that there's lots of natural ways to get near degeneracies. So you would think in principle that unconventional superconducting phase diagrams would be likely to be multi-phase. And this is something that's bothered many of us for years, because for 30 years, we only had UPT3 and some doped uranium beryllium-13 that were proven to have those kind of phase diagrams. Now, in the traditional way that buses always come together at once, 30 years later, in the same year, we now have two superconductors, the one I'm telling you about, and uranium tellurium 2, which is generating a lot of interest, which finally also have multi-phase superconducting phase diagrams. For cerium rhodium 2 arsenic 2, though, that is far from the end of the picture, because we don't have anything to say about the mechanism of the superconductivity. We don't have anything to say about its relationship to quantum criticality and the associated quantum fluctuations. And we don't have anything to say about the potential, well, the ordering that seems to be going on in the normal state, which we think might be multipolar. So in some senses, we've deduced a lot, I would say, and I'm very excited about the result, but this is only the beginning of research into this material. And I think it could prove to be something of a benchmark for this idea of local inversion breaking and its effects on superconductivity. So there's my summary. I always say, I hope that my summaries are clear if you've been able to follow the talk, so I won't read it out. I'll stop talking there, and thank you for your attention.